All right, here we are. This is lesson number 1 in our unit on electricity and magnetism. And we begin by talking about electric circuits. And that's kind of the first half of this unit. So we can mention the basics of electricity before we begin, but most of this you would have seen in grade 9. And so the basics of electricity, really, if we're going to talk about this, is that really electricity is the flow of electrons. We've talked in this about nuclear physics and how that has to do with the nucleus of atoms. Electricity has a lot to do with the electrons that surround the nucleus. So electricity is really another form of energy, electrical energy. This helps us basically to do work in the same way. Charge is another concept that we've learned about, that charge is basically either a buildup, an excess, or a deficit of electrons. But protons, in general, have a positive charge. Neutrons have a neutral charge, and electrons have a negative charge. So, really, we've investigated neutrons and protons, but now we're going to look at electrons and what happens when these electrons start zipping around. So, because electrons are so small, though, it's really impossible to count individual electrons or even to consider individual electrons. So what we do and what scientists have done in the past is that they kind of bundle electrons into these packages, and one bundle of electrons is given a unit name of a coulomb, and that's happens to be our unit of charge, is the coulomb, and we give charge a symbol of Q. Okay, so the overall charge on any object is determined by looking at the number of electrons that exist on that object times the charge on one electron. Okay, and what we know is that Q is the amount of charge in coulombs, N is the number, and E is this electronic charge, and that's 1.602 times 10 to the negative 19 coulombs. Okay, so this is the charge on one electron. If you're interested, read this. This is about how Robert Millikan found the charge on one electron, and it's very interesting. More on that in grade 12. Here's an example. A responsible student doing his laundry put his wool socks and a t-shirt into the dryer. When he took them out of the dryer, he noticed that they were stuck together because of this electrostatic force. If 3.7 times 10 to the 24th electrons were transferred from the socks to the t-shirt, what's the charge on the t-shirt? All right, well, we know that this t-shirt now has 3.7 times 10 to the 24th electrons. And we know what the charge on one electron is. It's 1.602 times 10 to the minus 19 coulombs. This never changes. So Q is equal to NE, and I make my substitution, and I solve. And I give this a negative sign because it means that the t-shirt has extra electrons on it, and so this t-shirt now is charged negative. So I get 5.9 times 10 to the 6 coulombs. Really, though, if we want to begin our investigation of electric circuits, and we do, in the first 2 lessons, we're going to kind of set up all the pieces that it's required to help us solve electric circuits. And so what we need to talk about first is current. And so we're going to turn our attention now to current. Later in the lesson, we'll talk about potential, which is basically the source that provides electrons with their energy. Current, though, is basically the flow of electrons. Current is given the symbol I, and its measure is charge per second. Okay, so electric current is coulombs per second, and that's the unit, or those are the units that we look at to define current. How much current flows through a hairdryer if 1,400 coulombs of charge pass through it in 2.25 minutes? Well, because I've got coulombs here, I need to turn this into seconds because I need everything to be in SI units. So I've got 135 seconds and I got 1,400 coulombs of charge. And if I take I is equal to Q over T, I get 1,400 divided by 135, and I wind up with 10.37 amps. An amp is a derived unit, and basically it's a derived unit. Instead of writing coulombs per second, we write amps. Okay, so this hairdryer would have a current of 10 amps. Moving along, If your nightlight uses a 7-watt bulb and it draws this much current, how much charge is going to pass through that bulb in 8 hours while you sleep at night? How much charge flows through? And if this is the charge on one electron, how many electrons pass through the light bulb in these 8 hours of time? Well, we know that here's the current that's flowing through that nightlight. And in 8 hours, given 60 minutes an hour and 60 seconds a minute, we have 28,800 seconds. So if the current is equal to Q over time, we can rearrange this and solve for the charge that passes through in the 8 hours. And indeed, it's quite a bit, 1.7 times 10 to the negative 3 coulombs. Now this seems small, but this is actually a substantial amount of charge. I can find the number of electrons by taking that charge in coulombs and dividing by the charge on one electron. And I find out that it's 1.06 times 10 to the negative 22 electrons. Here we see an introduction to the direction of current flow. And for a long time, people thought that current was the flow of positive charge because they didn't really know what an electron was. They didn't really know about what made up atoms. But they knew that there was this thing called electricity, and they knew that it kind of flowed in circuits. But they thought it may have been the flow of positive charge. And so that's called conventional current. Okay? So anytime when we're talking about conventional current flow, that's the flow of positive charge. We now understand, however, that current is actually the flow of these electrons, which are negatively charged. So in this course, we're going to consider current as the flow of electrons, unless we're going to note, unless basically we say otherwise. But for the most part, we're going to consider that current flow is electrons. So that's just a note. So let's talk about potential as a different part of this lesson. We've kind of talked about current and addressed that. Let's talk about potential. We know that charge doesn't flow on its own. Electrons don't flow all by themselves. They need some source of energy to get it moving. And work is done by a power supply to increase the electric potential energy of each coulomb of charge from a low value to a high value. And so as charge flows, its energy decreases. So here we have the potential is equal to energy divided by charge. So V is defined as this electric potential difference. And we see this measure of V when we look at batteries, right? And so a battery typically is 1.5 volts, but I'm sure you've seen those square 9-volt batteries, and very often you may be familiar with the 12-volt batteries that are in car engines. So all of these have this voltage, which really is how much energy is given to each coulomb of charge, or how much energy that battery gives to each coulomb of charge. And so let's talk about that. What's the potential difference across an air conditioner? If 72 coulombs of charge transfer 8.5 times 10 to the 3 joules of energy to the fan and compressor. So here we have this massive amount of energy, 8.5 times 10 to the 3 joules, and it's basically being distributed amongst this 72 coulombs. We want to find out what the potential difference across this air conditioner is. So I know the charge, and I know the energy that's being used. And so I could say, okay, potential is equal to energy over charge. And I can make this division here. And I get 118.06 joules per coulomb. Just like amperes, we didn't measure it in charge per second. We measured it in amps, right? That was for current. Voltage also has a derived unit. It's called the volt. And we give it a capital letter V. So this would be 118 volts. Okay. A static electric shock delivered from student A to student B transfers 15 joules of electric energy through a potential difference of 500 volts. So how much charge was transferred in that spark? So the potential difference between the two students is 500 volts. 15 joules of electrical energy were transferred. How much charge is that? So I got 500 volts and I got 15 joules. I can, of course, rearrange. 0.03 coulombs is what's transferred. Sometimes we want to know how much energy is available in a circuit to be transferred to a device. And so basically the energy delivered to the load depends on the potential and the rate at which energy is delivered, okay? So here we have E is equal to VIT, and this is a very common, very common equation to give us electrical energy. So here, E is the energy in joules, V is the potential difference in volts, I is the current in amps, and T is the time in seconds. So this would be the total amount of energy that's available in a circuit given a certain amount of time. So here's a very typical example. A 1.5 volt battery runs a portable MP3 player. And that MP3 player draws about 5.7 milliamps of current for about 6 hours. And then that battery is going to die out. So how much energy is available in this amount of time before, like how much energy does that battery transfer? Because this is basically what's happened is that we've got 1.5 volts that's giving this much current for 6 hours, and then it runs out. How much energy is that? Like, what are we talking about? Well, there's a couple things that we know. Of course, 60 minutes in an hour and 60 seconds in a minute, 21,600 seconds. And if I say E is equal to VIT, and I multiply these things out, I get 1.8 times 10 to the 2 joules, so about 180 joules of energy are transferred. A coffee maker draws about 5 amps of current for 270 seconds. It uses about 1.6 times 10 to the 5 joules of energy. What's the potential difference across the coffee maker? And here we can say, okay, well, I know energy, I know time, I know current, I know voltage. And I say, well, E equals VIT. I can certainly find V. Once I make all my substitutions, find voltage is equal to 118.5 volts. Of course, it's just a simple division here. Potential difference across a coffee maker, 120 volts.